Okay, now we've moved on to chapter 21.5. I'm going to separate 21.5 into several videos. The first one, I'm going to come back here and take a look at my book. The first one is going to concern kinetic versus thermodynamic enolates. I don't know if you heard that. 21.5 is going to be separated into several videos. The first one concerns kinetic versus thermodynamic enolates. All right, so the starting position here is 2-methyl cyclohexanone. Okay, so that's the one position. The two position then would have the methyl, so in the 6-membered ring with a ketone, so 2-methyl cyclohexanone. O-N-E for the ketone. Okay, so if we treat 2-methyl cyclohexanone with a base, we can pull off an alpha proton, and it turns out there are several different kinds. So, all right, there's that one, so the blue one, and then there's 2 of the green ones. And so the question is, which one does the base pick? They're really pretty close to the same acidity in terms of they're both on a carbon bonded to a carbonyl, so they're both alpha. They're all 3 alpha protons. We've gone over kinetic versus thermodynamic products in the past, and so remember the question is always the kinetic product always forms first. It always forms first. The question then is it reversible? So I'm just going to give this to you. So this is kinetic. This is going to be the kinetic enolate. And that makes the blue proton coming off the thermodynamic enolate. Okay, so we can get to that with a couple of different thoughts. First, there's 2 of these protons. Okay, so if a base is just randomly colliding with this molecule, it's twice as likely to collide with this proton than it is the blue proton. So that would, statistically, if the 3 H's all came off to give equally stable, if they were equally accessible and they gave equally stable compounds, you would expect 2-to-1 green to blue. But then there's another feature. They're not equally accessible, right? This blue proton, if a base is going to come in here and grab that blue proton, it's going to sterically encounter the methyl group. And so that blue proton is more sterically hindered than the green protons. And that gets big, that's a bigger difference the bigger this group is. There's less around these protons, and so the base can come in and grab those protons just fine. And so if a base is going to come in and grab a proton, it's always going to pick one of these green ones first. You're going to make that. And so the question you have to answer is the kinetic intermediate reversible? Okay, so let's look at this down below. Let's use hydroxide as the base. Okay, this is going to necessarily be in water, and you might try this for a simple Diels-Alder. I have no idea what chapter I'm in. You might see this for a simple alkyl. All right. So kinetic. So this is our kinetic enolate, and we get water. And so now the question is, does this back reaction happen? Okay, well, so the pKa here is about 19. pKa here is 15.7. So yeah, not only does the back reaction happen, this side of the equation is favored at equilibrium. So what that means is, ultimately, hydroxide is going to come in and pull this one. So right, this equilibrium is going to be established. Hydroxide will eventually pull the other one off and give you this. But now, so the other is, you got to remember this. Thermodynamic product, in order to have a difference, in order to see two different products depending on conditions, kinetic versus thermodynamic enolates, or products in general, the thermodynamic product has to be more stable than the kinetic. If the most stable product forms fastest, that's just the product, right? It won't matter what the conditions are. It forms, there you go, you got the most stable thing, you're stuck there. So the question is, if we go back up to here, is what I've called the thermodynamic enolate more stable or less stable than the kinetic enolate? And the way you're going to answer that is based on the alkene. So this is a tetrasubstituted alkene. And this is a trisubstituted. Okay, so yeah, if you consider these enolates alkenes, and there's a good reason to do that, that's really kind of what they look like. The tetrasubstituted alkene is more stable than the trisubstituted alkene. So yeah, this is the thermodynamic enolate, and you'll see a difference based on the conditions. So, right, if you draw a reaction energy diagram, let me put the colors we're using here, right? So the green one. The green is for the kinetic enolate. Green is going to form fastest. Remember, the enolate is going to be higher in energy than the starting material. Okay? So that's the kinetic curve. That's the kinetic enolate. The thermodynamic enolate is in blue. So I'll Okay, so thermodynamic enolate has a higher activation of energy, so it forms slower. But once it forms, it's more stable. The kinetic enolate has a lower activation energy, and so it forms faster, but then it's less stable. And so if you let all this equilibrium happen, right, when there's a crossing like this, if you let this all equilibrate, you'll end up down here. Now, I'm going to erase this and replace, well, I'm not going to erase it all. I'm going to replace the base. Okay. So now let's say that we use LDA at minus 78 degrees. All right, so it's cold. Now LDA, again, here's the structure of LDA. Takes this proton. Sorry. All right, so there's the base, and it takes this proton. You also wind up with NH. All right, so now look at pKa's. pKa here is, again, about 18. The pKa of diisopropyl amide is 34. And so now you ask yourself, does the back reaction happen? And the answer is no. Right? The conjugate acid of diisopropyl amide is roughly 16 orders of magnitude more stable than the ketone. Okay, so the equilibrium here, the equilibrium constant for this reaction is going to be like 10 to the 16th to the right. If you're keeping this cold, there's going to be very little back reaction. Right? So you're going to end up with the kinetic enolate. You're not going to see any of the thermodynamic enolate under these conditions. Here, the way this really looks now, right? This is way up here, comes down like this. Okay, so the kinetic enolate forms. and it basically just gets stuck there. You can't get there. You can't get back. So let me summarize that. Okay? So you should expect the kinetic enolate, if you're using a really strong base, at low T, low temperature. All right, you should expect the thermodynamic enolate when using weaker bases, or when you're doing these reactions under a higher temperature, right? Even if I use LDA, if I make a whole pot of enolate with LDA and I raise the temperature up to room temperature and I just let it stir for a while, sure, I can get some thermodynamic enolate. You can get some proton transfer. If you either have excess base or if you have excess ketone, you can get some proton transfer that results, remember, the way to get kinetic enolate is you don't let the reaction equilibrate. If you let the reaction equilibrate, you're always going to see the thermodynamic product. So you want to prevent it from equilibrating. Okay, and you'll see examples of this as you work problems and we look at other molecules that we can enolize.